Look at a textbook diagram of a distributed key-value store. You'll usually see a perfectly symmetric, endlessly spinning ring of servers. It looks flawless. A client sends a request to a proxy called a coordinator node, which maps it onto a consistent hash ring, distributing data evenly across multiple servers. To ensure availability, the data is replicated to multiple backups across the ring. This architectural model assumes a state of operational perfection that rarely exists in a real-world environment. It relies on the premise that physical hardware and network connections function flawlessly, 100% of the time. In a massive production environment, servers spontaneously catch fire, network switches fail, hard drives degrade, replicas silently fall out of sync. Reliable engineering requires treating a distributed system as a mechanism in a state of constant, managed degradation. Success depends on building the internal logic to navigate that decay. The first architectural hurdle is diagnosis. How does a cluster actually verify that a specific node has died, rather than just experiencing a momentary network delay? Look at this diagram. The naive approach is all-to-all multicasting, where every node continuously sends a heartbeat ping to every single peer in the system to check its pulse. This works for 4 servers, but if you scale this to 10,000 servers, those simultaneous pings completely saturate your network bandwidth. The diagnostic tool itself brings the system down. To fix this, large-scale systems use a decentralized mechanism known as the gossip protocol. Here is how it operates. Each node maintains a local membership list containing the heartbeat counters of its peers. Every second, a node updates its own counter and sends its list to just a few randomly selected neighbors. If a heartbeat hasn't increased in a set period, that specific member is flagged as offline. When those random neighbors receive the list, they update their own records and forward the news. The information spreads exponentially. Node S0 learns that S2 is down from an independent peer, marks it offline, and routes around the failure. By decentralizing failure detection, the system eliminates the need for a master diagnostic node. The cluster acts as a self-monitoring organism. Once a failure is detected, an immediate crisis follows. A client is trying to write data right now, but gossip just confirmed the required target node is dead. If the architecture uses a strict quorum, meaning it rigidly demands all assigned replicas acknowledge the write, it rejects the user's request. The system protects its data structure, but destroys its availability. This diagram shows a workaround called a sloppy quorum. Instead of enforcing the strict requirement, the coordinator node ignores the offline server and writes the data to the next healthy server, node S3. Node S3 isn't supposed to hold this data long-term. It acts as a surrogate, using a process called hinted handoff. The system stores the write alongside a specific instruction. Deliver this payload to node S2 the moment it wakes up. When the gossip protocol eventually detects that node S2 has rebooted and is accepting traffic again, the surrogate automatically pushes the accumulated data back to its rightful owner. Sloppy quorums preserve the client's ability to save their work, maintaining high availability, but they intentionally create temporary data inconsistencies that the cluster must continuously track and repair. Temporary handoffs work for reboots, but if a hard drive fails entirely or silently drops a write request, the replicas experience permanent divergence. Repairing this requires synchronization, but transmitting and comparing every single key across billions of records between 2 servers would paralyze the network. Look at this structure. To find the error without transferring raw data, the system divides the vast key space into manageable buckets. Here, we can see a single discrepancy sitting in bucket 8. To find that error efficiently, the system uses an anti-entropy protocol built on Merkle trees. Each bucket of data is run through a hash function, building upward to a single root hash. During a consistency check, the servers only compare their top root hashes. If those match, both servers know their underlying data is identical, and the check ends instantly. But if the root hashes disagree, the system traverses downward, checking the child nodes. It ignores the branches that match, following only the red, mismatched hashes all the way to the bottom. Once the exact conflicting block is isolated, the servers exchange only that specific piece of data to overwrite the error. Merkle trees allow a database to identify a single corrupted kilobyte hidden inside terabytes of data, synchronizing the cluster with extreme precision. Localized errors are minor compared to a total data center outage. Power grid failures and natural disasters can wipe out an entire geographic region at once. This diagram illustrates a multi-data center failover. When US West goes dark, a GeoDNS service detects the massive drop in heartbeats and immediately diverts 100% of the global application traffic into the surviving US East data center. Suddenly, every individual server in the surviving region has to process double its normal load. Let's look at the microscopic architecture of a node fighting to handle this crush of requests. Here is the write path of a Cassandra-style node. To prevent data loss if this server crashes under the strain, the incoming write is immediately appended to a sequential commit log on the physical disk. Simultaneously, the data is loaded into a fast in-memory cache. Once that cache reaches its capacity limit, it flushes the sorted batch of data downward, writing it into an immutable SS table block on the disk. When a client executes a read request, the node always checks that in-memory cache first, looking for a fast, frictionless hit. But if the data isn't in memory, the node has to search the physical disk. Scanning through thousands of frozen SS tables to find one specific key is a massive, slow bottleneck. This is the read path during a cache miss. To bypass the bottleneck, the node checks a Bloom filter, a probabilistic data structure that instantly tells the system which exact disk file holds the required key, completely eliminating the need to search. Even down to the sector level of a single hard drive, every step of the architecture is designed to predict bottlenecks and maintain raw operational speed under heavy duress. Consistent hash rings, gossip protocols, sloppy quorums. Hinted handoffs, Merkle trees. We have layered an incredible amount of complexity over simple read and write commands. This diagram reveals why all this machinery is necessary. The CAP theorem. It states that in the presence of a network partition, a distributed system must sacrifice either perfect data consistency or high availability. If you lower your read and write quorums, your application stays fast and available even when data centers burn down, but you risk temporarily serving stale data to your users. If you demand strict quorums, every user gets perfectly consistent data, but the application will stall out and block transactions the exact moment a network switch drops a packet. In systems architecture, there are no perfect solutions. There are only engineering trade-offs, and business leaders must decide which penalty they can afford to pay. A production-grade database remains stable only by constantly executing these background repair tasks to mitigate the effects of hardware and network entropy.